Hello everyone, thanks for watching this video recording. In this video recording, I will discuss our recent paper accepted at the HSCC conference. My name is Sadek Sujani. I'm with the School of Computing at Newcastle University. This is a joint work with Rupak Majumdar from Max Planck Institute for Software Systems. In the paper, we provide some results on computability of basic problems studied classically in control theory, including linear quadratic regulator and linear quadratic Gaussian control. I start by some basic definitions which might be new for the audience in control community. The first one is the difference between algebraic numbers and transcendental numbers. Algebraic numbers are roots of polynomials in one variable with rational coefficients. Examples of these numbers include integers, rationals, a square root of 2, the fourth root of 3, 1 plus a square root of 2, and so on. We can easily write down a polynomial with one variable with rational coefficients such that their roots are the numbers I just mentioned. Other numbers are called transcendental. Examples of transcendental numbers include the Euler number e, pi, 1 minus pi, a square root of e, and so on. In general, establishing whether a number is algebraic or transcendental is a difficult task. For example, we don't know if pi to the power Euler number is algebraic or transcendental. We don't know if e plus pi is algebraic or transcendental. Another point that I want to discuss in the beginning is the definition of a decision problem. Decision problem is a problem that can be posed as a yes-no question of the input values. Examples of decision problems include controllability and observability of dynamical systems, because in controllability we ask whether a given dynamical system is controllable or not. The same thing for observability. So it's a yes-no question. When we talk about decidability of decision problems, we mean if there is an effective procedure to determine the answer of the problem for any given input. So we are looking for an effective procedure that gives us a yes-no answer to the question. And the effective procedure should consist of a finite number of exact finite instructions. It should always terminate after a finite number of steps, and it always produces a correct answer. And in principle, it can be done by a human using only writing materials. Okay. The main motivation of our work was related to the fact that many fundamental problems in the theory of linear systems involve transcendental functions. So you need exponential function, sine and cosine functions to get the closed form of the solution. These problems can only be evaluated numerically despite having a closed form solution. And in general, it is possible that numerical imprecisions prevent answering the decision problem, no matter what precision is used for the computations. So the computability of these natural decision problems has remained open. To give you an example of such decision problems, suppose you have a simple linear dynamical system, x dot equal to a times x, and you are given a set of initial states, a set of bad states, and a time bound capital T. The question is whether there is a trajectory from some initial state to some bad state within the given time frame. It's a reachability problem, and we do not know if this problem is decidable. We do not know if there is an effective procedure that can give a correct answer to this reachability question. Okay, the main contributions of our work is the following. The decision problems associated with LQR and LQG are decidable, and the decidability is not relative to any given limit on the numerical precision. The proofs we are using are based on the Lindemann-Weierstrass theorem from transcendental number theory. We want to judge zeros of exponential polynomials in the closed form solution of these problems. We also provide conditional decidability results for several open problems, including controllability of time-varying systems and guaranteed transient bound for linear autonomous systems. Here is the outline of the rest of the presentations. First, I will discuss some initial observations that lay down the rest of the results. I will discuss decision problems for LQR and LQG. I will provide conditional decidability of several open problems. And finally, I will end the presentation with some concluding remarks. Let's start from the linear time invariant system, x dot equal to a times x. The initial condition is x0, and we know there is a closed form for the solution of this system. X at any point in time, the trajectory at any point in time is given by e to the power at times x0. So e to the power at is just exponent of a matrix, which is multiplied by x0 to give us the value of the trajectory at time t. This closed form representation means that we can represent each coordinate of the trajectory as a summation of exponential functions multiplied by polynomial functions of time. So these exponential functions are constructed based on the eigenvalues of the A matrix. So we write down an equation, the characteristic equation of the A matrix, which is the determinant of lambda I minus A equal to 0. The zeros of this equation are eigenvalues of A, and these eigenvalues are appearing as a coefficient in these exponential functions. And we also get some polynomial matrices here, which are polynomial functions of time constructed using the Jordan form of A. So this means if we start the definition of the system with some algebraic matrix A, and we want to evaluate the trajectory at some algebraic point in time, then each element of this matrix, e to the power at, can be written as a finite sum of this form. It becomes a finite sum, which is equal to the summation of alpha j times e to the power beta j, and these alpha j and beta j are algebraic numbers. Why is this the case? Because once we know that A is algebraic, the solution of this polynomial equation becomes also algebraic. So all these coefficients here are algebraic, the time point is algebraic, and the exponent here becomes an algebraic value. The same thing holds for the evaluation of these polynomials at an algebraic point in time. Okay, so then once we get this representation, we know that deciding whether the trajectory is greater than some threshold at some particular point in time is decidable. So there is an effective procedure that tells us whether this inequality holds or not. So in the next slide, I will show you how we can establish the decidability of this simple inequality related to the solution of the linear system. To establish this, the decidability of this inequality, we need a theorem from Lindemann and Weierstrass, and it's essentially telling us how to judge equalities that involve exponent of algebraic numbers. Suppose you have some distinct algebraic numbers, alpha 1 until alpha n, and if you want to solve such an equation and you know that the coefficients are also algebraic, so the coefficients C1 until Cn are also algebraic, then this equation has only a trivial solution, and it holds only when the coefficients are all equal to 0. Yeah. So this Lindemann-Weierstrass theorem is very strong in the sense that it gives us a way of checking equalities of this form. To check whether this equality holds or not, we can just simply check the values of the coefficients and check whether all of them are equal to 0 or not. Now let's make this a bit formal and look at the inequalities. Suppose you have an exponential polynomial, here p. So an exponential polynomial is just a polynomial that you replace some of the variables with exponential functions. You see, this can be seen as like a polynomial of 2n variables, and you replace n of these variables with exponential functions of the variables x1 until xn. So this is an exponential polynomial, and suppose I want to evaluate this exponential polynomial at an algebraic points, so alpha 1 until alpha n are algebraic. And the problem of deciding whether the value of this exponential polynomial at this point is greater than or equal to r is decidable. How does it work? Because first I can check equality. I can put the equality sign here, and then I reorder all the terms in the left-hand side and the right-hand side. I get an expression like this in the Lindemann-Weierstrass theorem. Then I can check whether the equality holds or not. If the equality holds, then the answer is clear. If the equality doesn't hold, then I know that the inequality could be strict. I go and use an approximation of the left-hand side with enough number of bits to check whether it's greater than r or not. Yeah? And since the inequality doesn't hold, the equality doesn't hold, I know there is a gap, and this gap is useful for finding the number of bits for the approximation of the left-hand side. So the main message of this slide is that if you have an exponential polynomial and you want to evaluate that exponential polynomial and compare it with the threshold, this task is decidable. You can always do this. Okay. So now let's see how this can help us in establishing decidability of LQR and LQG. Okay. So this is the definition of LQR. You have a linear dynamical system, x dot equal to a times x plus b times u, starting from some initial state x0, and you have a quadratic cost function over some time interval from 0 until tf. You have a quadratic function of the state, a quadratic function of input, and you have a terminal cost associated with the final state of the system. And these matrices S, Q, and R should be positive or semi-positive, positive definite or positive semi-definite. Okay. So now the decision problem asks whether there is a controller such that the cost of this optimal cost is less than or equal to some threshold. So here I assume that all the matrices characterizing the problem are rational. So A, B, Q, R, S, initial state, and the threshold. These are all rational, and I ask whether there is a controller such that the cost associated to this controller is less than or equal to R. And here is the result that says the LQR decision problem is decidable. Now let's see how we can establish the decidability of this problem. First, I look at a characterization of the solution. So the optimal solution to the LQR problem is in the form of a state feedback. So I have u of t equal to a gain times the state of the system. The gain depends on a time-varying matrix, kt, and kt is usually computed numerically by solving a Riccati equation. So this is the Riccati equation. It's nonlinear. It is solved backward in time, starting from the final time point, ktf equal to s. And by solving this equation backward in time, we get the value of the gain matrix k at 0. Once I have k at 0, I get the expression for the minimal cost associated to LQR problem. But this representation is not useful because it doesn't give us a nice representation for the solution of this nonlinear Riccati equation. We can use another representation of the solution, which is the multiplication of two matrices for k. So k is equal to multiplication of lambda times x inverse. This lambda and x should satisfy the Hamiltonian differential equation. So it's a linear differential equation with some particular matrix H here. If all the matrices A, B, R, and Q, these are rational, this H is also rational. That's why the solution of this differential equation becomes in the form of an exponential polynomial, and the entries of kt and the optimal cost function becomes ratios of exponential polynomials because we have lambda times the inverse of x. Lambda and x are exponential polynomial, k becomes the ratio of an exponential polynomials, and deciding whether this ratio is greater than or equal to some threshold is decidable because we can just multiply both sides by the denominator. It becomes an inequality on exponential polynomials. Okay. The same methodology can be applied to LQG decision problem. Suppose you have the stochastic system that is affected by Brownian motions. We have a Brownian motion that affects the evolution of the state, and we also have some measurement of the state, which is also affected by another Brownian motion. And the covariance matrices of these Brownian motions are known. The initial condition is also normally distributed with some known covariance matrix, and the LQG problem asks us to find an estimator such that the variance of the estimation is minimized. The decision version of this problem asks us to check whether the least square error of the estimate is less than or equal to R. So instead of computing the least square error, we want to check whether the value, the least square error, is less than a threshold. And we can show that this LQG decision problem is decidable. The line of reasoning is similar to LQR. We start from the closed form representation of the estimator, which is the Kalman filter. There is a gain in the Kalman filter, which can be computed using a Riccati equation. The Riccati equation is solved forward in time, but it's nonlinear. It's not useful for us, but the solution, the least square error, is just a trace of the solution of this Riccati equation. What we can do is to use the Hamiltonian representation of the solution. So we can write this matrix P as the multiplication of lambda and x inverse. Lambda and x are solutions of an Hamiltonian differential equation. That's why they become exponential polynomials, and this matrix PT and the least square error becomes ratios of exponential polynomials, and comparing these quantities with a threshold is decidable using the Linemann-Weierstrass theorem. Okay. So now I go with some conditional decidability of open problems that are a bit more challenging compared to the two problems that I just discussed. Let's extend LQR and LQG decision problems with some minor modifications. So the modification I want to perform is that I want to quantify over x0 and allow x0 to change inside some set. Suppose I don't know the initial state of the system, but I know there is a bound on the initial state. I want to check whether there exists some initial state inside this set capital X0 such that the cost of the LQR is less than or equal to R. The same modification I can apply to LQG. Instead of fixing the covariance of the initial state, I allow the covariance of the initial state to vary inside some set, and I want to see if there is a covariance inside that set such that the least square error of the estimation is less than or equal to R. So these problems do not fall within the purview of our decision procedure because we existentially quantify over x0 and p0. To establish decidability of these problems, we need stronger tools from transcendental number theory because reasoning about zeros of exponential polynomials is challenging, and the tool I'm using is Shanwell's conjecture. So Shanwell's conjecture says that suppose you have some complex numbers a1 until an that are linearly independent over rational numbers. If you take the exponent of take the exponential of these values a1 until an, e to the power a1 until e to the power an, so you have 2n numbers. Among these 2n numbers, at least n are algebraically independent. So this is the claim of the conjecture. We don't know if this conjecture is true or not, and it is believed to be a difficult result to prove, and it's believed to imply many known results in transcendental number theory, as well as all reasonable conjectures on the values of the exponential function. So this conjecture has a major role in the related literature. One of the nice things about this conjecture is that if we restrict the inputs like a1 until an to be algebraic, we get the Lindemann-Weierstrass theorem. So it's a kind of generalization of the Lindemann-Weierstrass theorem, but we don't have any proof for this yet. If this conjecture is true, we get the decidability of the theory of reals extended with exponential sine and cosine functions over bounded domains. So this result is proved by McIntyre in lots of collaborations with Wilkie in 2008. If we assume Shannon's conjecture and we write a statement by existentially quantifying over variables or universally quantifying over them, and we use exponential sine and cosine functions over bounded domains, then that statement becomes decidable. And this theorem is a powerful tool to prove conditional decidability results for many problems in linear system theory. Okay, let's see how we can use this to have conditional decidability of extended LQR and LQG. Suppose you have LQR problem with a polytopic initial set. That problem is decidable subject to Shannon's conjecture, and the proof is to write the characterization as a statement in that extended theory of reals. So we want to see if there is an x0 belonging to some region such that the cost is less than or equal to r. The cost is ratio of exponential polynomials, and we have some additional variables, and these variables belong to some polytopic set with algebraic matrices. That's why it becomes decidable subject to Shannon's conjecture. The same thing holds for LQG with polytopic initial covariance, which is decidable subject to Shannon's conjecture. Let me introduce another two problems. The first one is controllability of linear time-varying systems. Suppose you have x dot equal to ax plus bu, but now these matrices A and B are not constant anymore, they change over time. This system is called controllable if there is an input to take the state from any initial state to any final state. And the controllability asks whether this LTV system is controllable, and here I restrict the problem into having A and B to be exponential polynomial functions of time. To establish decidability of this problem, we need a result from Zondak, proved in 1998. It says that if you want to check controllability, we have to construct a matrix B0, B1 until Bn minus 1. So these Bi's are dependent on time, and they are constructed using differentiation and multiplication on the two matrices A and B. If A and B are exponential polynomials, this matrix also becomes an exponential polynomial. To check whether the system is controllable, we should check whether this matrix can be full rank for some point in time inside the given interval. And if we assume Shannon's conjecture, checking whether this matrix has a full rank at some point becomes decidable, because at the end we have to take the determinant of some submatrices of this big matrix and check whether that determinant could be 0 or not. Okay, and this is decidable subject to Shannon's conjecture. And this is the last open problem I discuss here, which is related to exponential stability of autonomous systems. Suppose you have x dot equal to a times x. This system is exponentially stable if I can find the two constant m and beta to satisfy this inequality here. So this inequality gives a bound on the decaying behavior of the dynamical system. So e to the power at gives us the solution of the dynamical system, and we want to see whether the norm of this e to the power at is less than or equal to a constant times e to the power bt, and beta should be negative, and m is a constant to make sure that the inequality is always true. We know that this exponential stability can be checked very easily by looking at the eigenvalues of the A matrix. Suppose gamma A denotes the maximum of the real parts of the eigenvalues of A. It is well known that if this gamma A is negative, we have the exponential stability. We just need to pick a negative value for beta, which is larger than gamma of A, and then we can always find a constant m to satisfy the inequality. But the open problem is to find the minimal value for m. Suppose I have A, suppose I have picked a beta. Now what is the minimal value for m such that the inequality holds. We can formulate the decision problem associated to this. We can start by having some upper bound for m as m0 and check whether there is an m less than or equal to m0 such that the inequality holds. And this problem becomes decidable subject to Shannon's conjecture. We should massage the inequality a bit to write a statement in the extended theory of reals. It's written here. I don't want you to look into the details, but it's just writing existentially quantifying over some variables and transforming the inequalities into some equalities using exponential sine and cosine functions. And then one of the challenges here is to make sure that all the variables remain bounded, because the extended theory works only with bounded variables. Okay. To conclude the presentation, I showed that results from transcendental number theory can be used to show decidability of problems in linear system theory. And the associated control and optimization problems have been studied extensively, but the computability status of these problems had remained open. Computability result is interesting because it answers whether numerical computations converge at some finite precision, or we don't get any, we might not converge no matter what precision. We might not get the correct answer no matter what precision is used for the approximation. As an extension, we can estimate computational complexity of the decision procedure using quantitative versions of Lindemann-Weierstrass theorem. These complexity bounds are pessimistic. They are doubly exponential, dependent on some proper representation of the input values. It would be interesting to see whether there are better computational complexity bounds. We are not aware of any lower bound on the computational complexity. It would be also interesting to see whether there are lower bounds for the complexity of these decision procedures. Thanks for listening to this video recording. Feel free to contact me if you have any questions. Thanks very much.